Today we are going to talk about something called the dot product of two vectors. This is an idea that's best motivated with a physical example. So let's imagine we have a line, and on this line we have an object, this lovely purple dot, and we are going to move this object, we're going to push it down the path some distance from the purple dot to the black dot. So we might put a vector on here to indicate the actual path that it will be following. I'll call that vector d for distance. Now, the easiest thing to do would be just to push the object parallel to the direction of motion, but let's do something more interesting. Suppose that we were to use a force that is at an angle to the direction of motion. Maybe the object is constrained to stay on this straight line path. Maybe it's like railroad tracks or something. But anyway, if we have a force that is at an angle to the direction of motion, there, maybe something like this, let's call that F. If you've had physics, you know how we resolve a situation like this. If you haven't had physics, I'll explain it right now. Because of that angle, not all of this force is actually doing work on the object and moving it down the path, only some of it. And to figure out how much of it, we decompose this vector into two parts, one of which is parallel to the direction of motion, and one of which is perpendicular to it. So that we can say that our force vector F is actually the sum of these two other vectors. I'll call this one F parallel because it's parallel to the direction of motion, and I'll call this one F perpendicular because it's perpendicular to the direction of motion. And now we can see that F is the sum of these two other vectors. Now the idea is that this component vector isn't actually doing any work moving the object down the path. This component is the one that's actually doing the work. And this word work has technical meaning in physics, with which you may be familiar. And the idea is that the work done by a force in moving a particular object through a particular distance is the product of the amount of force and the distance itself. And when I say the amount of force, I just mean the component of the force in the direction of motion. So in this case, for example, the work done by force F on the object in moving it along vector d would be the product of these two things. Right? The length of that vector, that's the force that's actually doing work, and the length of that vector, the distance through which the object is traveling. So the work here would be the length of F parallel times the length of d, and that's how you would compute it in physics. And if you take a physics course, you'll find much more about work. Here I'm just using it as a motivating example because what we've just done is actually compute a dot product. I'll explain how now. Forgetting about any kind of physical context, if I have two vectors, v and w, label them as such, v and w, then we define what is known as the dot product, which we write v dot w, as follows. It's going to be a product of two numbers. The first is what I'll call the scalar projection of v onto w, and the second is going to be just the length of w. So what do I mean by the scalar projection of v onto w? If I drop a perpendicular here, and I think about this length right there, that's all I mean by the scalar projection. Scalar because it is going to be a scalar, not a vector. So, for example, to make this numerical, let's just say that that length right there is 2 units. And let's say that the length of w itself is 5 units. In that case, v dot w would just be 2 times 5, which last time I checked is 10. And similarly, if we had some other pair of vectors, maybe looking like this, and let's call one of them A and one of them B, and we wanted to look at the dot product A dot B, we would have to think, well, what is that? That's the scalar projection of A onto B times the length of B. And just eyeballing these things and making up some numbers, we might say, okay, scalar projection of A onto B that's pretty small, right? If we take that right there, if we drop a perpendicular, let's just say that that's 1 unit. So then we might have something like this is equal to 1, and let's say that the length of B, who knows, is 3. In that case, the dot product of A and B would be 3. That's almost all there is to the definition of the dot product. There's one last thing we need to note, which is this. It's a little more interesting if we have two vectors and the angle between them is obtuse, like this. Okay, so let's say this is vector v and this is vector w, and we're interested in v dot w. We think we know how that works. That's going to be the scalar projection of v onto w times the length of w itself. The only problem here is that first factor, the scalar projection of v onto w, because we have to actually project v down onto the extension of w backwards. Right? That's going to fall down here. Now, that's going to have a certain length. Let's just say that length is 2. And what we do when we talk about the scalar projection of v onto w, we are going to take the negative of that length. We would say negative 2 in that case, because v falls on the wrong side of w, as it were. So its shadow falls 2 units behind w, rather than 2 units along w, like that. Anyway, we're going to multiply that by the length of w, and for the sake of argument, let's say that's 9, so that we would end up here with minus 2 times 9, which is minus 18. And we end up with a negative dot product. You can see how this makes sense in terms of the earlier example, the physical example, with work. If, say, we were trying to move this object down this path, and we were using this force to push it, well, we'd be pushing it in the wrong way, which is why we end up doing negative work on the object. So work is a nice example of dot product, but dot product comes up all over the place in geometry, which is mostly how we will be using it in this class. And our first order of business is going to be to develop some basic properties of the dot product, some of which will be algebraic, some of which will be geometric, and we will stitch them all together. So let's get started with the first one. The first question about the dot product we might ask is it commutative? Is it true that it doesn't matter about the order, right? We don't know. It's not at all obvious that the dot product should be commutative, and we know not to take that for granted. And we can just think about this geometrically, what's going on. If we are thinking about the left-hand side here, v dot w, well, what is that? That involves the scalar projection of v onto w, right? This length right here, put that with a green line like that, that times the length of w itself. The product of the green line and that would be v dot w. On the other hand, what about w dot v? That would be the projection of w down onto v, let's put that maybe in its own color, red, times the length of v. Are those two things going to be equal to one another? Some of you may have spotted why this is so already. Look at our picture here. I have a right triangle here and a right triangle here. I have two right triangles, and of course they share this angle right here. And two triangles with two angles in common are necessarily similar. And why do we care about similar triangles? Because we know their proportions are the same. Let's look at the ratio of the leg adjacent to the purple angle to the hypotenuse. On the small triangle, that ratio is going to be the leg adjacent to the purple angle is red, and the hypotenuse is just the length of w. Now, by similar triangles, I know that the ratio on the large triangle is going to be the exact same. Well, on the large triangle, what is that ratio? First, we were looking at the leg adjacent to the purple angle, which in terms of the big triangle is the green side, and then we were looking at the hypotenuse. And the hypotenuse of the big triangle is just the length of v. Well, if we clear the fractions in this case, we get the red stuff. This is very careful mathematical notation, you understand. The red stuff times the length of v is the green stuff times the length of W. That is, what is that stuff on the left? Red stuff times length of V, that's W dot V, based on our definition of dot product. And the green stuff times the length of W, well, that is just V dot W. Lo and behold, thus the dot product is commutative. Hallelujah. To be perfectly rigorous, we would also want to consider the case where the angle between the two vectors is obtuse, and I'll leave that for you to work out. Once again, you can do it just with elementary geometry. The next property is something that we will use all the time in this course, and you will use all the time whenever you use the dot product in any other class. It's this. Two vectors are going to be perpendicular to one another if and only if their dot product is 0. You can see why this is so very easily. Let's draw a couple vectors on here. So here's one. Let's call that one V. Here is another one. Well, first of all, let's just draw them perpendicular to one another. If they're perpendicular to one another, what do we know about their dot product? We know we can do it in either order. V dot W is the same as W dot V. So if we're looking at, say, W dot V, that's going to be the scalar projection of W onto V times the length of V. But what's the scalar projection of W onto V? It's going to be nothing. It's not going to cast any shadow whatsoever. It's going to be 0 times the length of V, which is, of course, 0. So we see that when two vectors are perpendicular, definitely it follows that their dot product is 0. What about the other way around? Is that the only case? My claim is not only that perpendicular vectors have a 0 dot product, but that if we have two vectors whose dot product is 0, then we know that the vectors must be perpendicular. It's easy to see why that is the case as well, because if the two vectors were in any other position whatsoever, okay, if they're not perpendicular, in that case, if we're looking at their dot product, clearly the fact that they are not perpendicular means that one of them casts a shadow on the other one, like that when we project it down, which means that the dot product of those two vectors is going to be the product of two non-zero vectors. Right? In this case, it would be a positive number, that scalar projection, times that length right there. But this would definitely be non-zero. So if we have two vectors whose dot product is 0, the only way that can possibly happen is if the vectors are perpendicular themselves. So this criterion for perpendicularity is something we will use all the time. So get used to the fact that a dot product of 0 means that you have perpendicular vectors, and if your vectors are perpendicular, that means the dot product is 0. It's also the case, as you can verify for yourself, that if the dot product is positive, that means that the angle between the vectors must be acute, as it is here, and if the dot product is negative, that means that the angle between the vectors must be obtuse, as it is right here. That's easy to see why by thinking about the stuff we talked about earlier. Okay. The third property of the dot product I want to talk about today is so simple that you might wonder why I even pointed out, but it turns out to be useful. It has to do with taking the dot product of a vector and itself. Taking a dot product of a vector and itself. If we have a vector v and we take the dot product of the vector and itself, well, we get the scalar projection of v onto v times the length of v. Well, if we project v onto v, we get the whole damn thing, which means that the scalar projection of v onto v is whatever the length of v is. And we're multiplying that by the length of v, so we end up with the length of v squared. Let me just summarize that. So this property right here, that the dot product of a vector with itself is the square of that vector, is something that we will often find useful. It gives us a way of passing from statements about dot products to statements about lengths, which is sometimes simpler, or vice versa. Sometimes when we see squares of lengths, we can turn that into statements about dot products, and then we can use properties of dot products that we'll be developing shortly. There's an associative property we need to look at as well. If we have some scalar multiple of a vector and we dot it with another vector, we can take that scalar multiple and just pull it outside of the dot product. It's not too hard to see why this useful property holds. I will give you a few hints in that direction right now. To see what's going on, think about this picture right here. which gives us a vector v and a vector w, and then this vector alpha v, a stretched version of that. I put those because those are the three vectors that actually appear in this formula, and we want to see why this equality holds. Now I have dropped these two perpendiculars from v and alpha v onto w and indicated their lengths with these colors because, of course, those are going to show up in the interpretations of those dot products. In fact, what we have, if we think about the left-hand side of our proposed equation, alpha v dotted with w, that is going to be this green length times the length of w. So I will write that in right here. That's the green length times the length of w. But there's an observation we need to make here about that green length. Look at these two right triangles. They are, of course, similar triangles because they are both right triangles and they share this purple angle. Since they're similar triangles, there's a common scaling factor for all of their sides, and that scaling factor is obviously alpha, because the hypotenuse of the big triangle is alpha times the hypotenuse of the small triangle. That means that exact same relationship has to hold right here. The green length has to be alpha times the red length, which means that I could rewrite this expression right here. Instead of the green length, I could say alpha times the red length times the length of w. So I've got the product of these three scalars right here. Well, I know that the associativity property holds for ordinary arithmetic of numbers, which means that I can shift those parentheses a little bit and write this as alpha times the red length times the length of w. And why do I want to do that? Because this stuff that's in the parentheses now, the red length times the length of w, that is obviously v dot w. And so, lo and behold, look what we have done. We have proved that alpha v dot w is the same as pulling the alpha out and having alpha v times w. That's exactly what we wanted to prove. So, QED, we have proved our theorem. By the way, what if the shoe is on the other foot? What if we have a scalar multiple of the second vector in the dot product? Does that change anything? Are we allowed to pull that beta out? Yes, of course we are. Thanks to the commutativity of the dot product, which we proved earlier, we know that we could rewrite that as beta w dot v, and then thanks to this property in the blue box up there, I can pull out the scalar beta and write it like that. And even if I want to, I could then turn around that w dot v and write it as v dot w thanks to commutativity again. So the net result being that I can take that and pull that scalar in the second slot out into the beginning. What if I had scalars in both positions? Like, let's just say, let's use some actual numbers. Let's say I had 5a dotted with 12b. Can I just pull those two things out simultaneously? Of course I can. If I wanted to be very fussy, I would pull them out one at a time and say that's 5 times a dot 12b. Then I could pull that 12 out and say that's 5 times 12 a dot b, and that's going to be 60 a dot b. Of course, in practice, you wouldn't write all of these details out, but I'm just showing you that you can do it. Right? In general, when we see something like 3a dot minus 2b, we will just write minus 6ab and be done with it. The next property of the dot product that is important is that the dot product distributes over vector addition, meaning that if I have three vectors, v, w, and z, and I form v dot w plus z, I can actually distribute that dot and end up with v dot w plus v dot z. This takes some work to prove, but you can actually do it with a picture. I'll put the picture up all at once. Okay, there is the picture. I encourage you to pause this here and spend some time thinking about this picture and how its parts relate to the parts of this expression. By playing around with them, you should be able to see why this picture demonstrates that this statement is true. I will leave that to you. Well, I'll give you one little hint to get you started. Look at just the left-hand side first. v dot w plus z. We know that's the same thing as w plus z dot v by commutativity. And we can actually read w plus z dot v right off the picture. Here's w plus z, the purple vector, and here is v. So the dot product of the purple vector and v is going to be the scalar projection of the purple vector onto v, which is this green length right here, times the length of v. So we have the green times whatever the length of v is. Now come up with similar interpretations for these two, and that should get you about 3/4 of the way through the proof. Okay, our next order of business is to come up with two different formulas for the dot product. The first one is trigonometric in nature and is very easy to derive. What we're going to end up doing is coming up with a formula for the dot product of two vectors in terms of the lengths of the vectors and the angle between them. So let me write down here. If theta is the angle between v and w, then v dot w is, and we can figure this out quite easily. Just basic trigonometry. We're going to drop a perpendicular right here, and we recognize, of course, that the dot product is going to be the product of this length right here and this length right here. But we know what those two lengths are. This one is going to be the length of w times cosine of theta, just by basic trigonometry, since, of course, the length of w is the length of w. And this one right here is, of course, just the length of v. And so when we multiply those two things together, we get the length of v times the length of w times cosine of the angle between them. And this is an important result right here. Some people even take this to be the definition of the dot product. And we'll see soon that this gives us a nice way to actually compute the angle between two vectors once we've determined our second formula for the dot product. Our second formula for the dot product is different. In this one, we're given the coordinates of two vectors. And from those coordinates, we want to actually compute the value of the dot product. Here's our derivation. v dot w, but what is that? v1, v2, that is just shorthand notation, we remember, for v1 I hat plus v2 j hat. And we're dotting that with w1 I hat plus w2 j hat. Now we can call on the various properties that we've established already. For example, we know that the dot distributes over addition. So what we're going to do is think of this as one block, and when we dot it with this sum, we're going to distribute it to the two terms. And when we do that, we end up with this. And what can we do from here? Well, we can do the distribution of the dot again, because here we have something, and we're dotting it with a sum, so we can distribute that dot. Same thing over here, we can distribute that dot. And when we do so, we end up with this. Now we've got these four terms, and we can use things that we know already to simplify this still further. For example, one thing we learned was that when we have a dot product, we can pull constants through the dot. So for example, that first term, by that associative property, if I pull both the constants through, I'm left with v1w1 I hat dot I hat. And on this next one, I'm going to end up with v2w1 j hat dot I hat. And so on with the other two terms right here. This is looking like a big expansive mess, but it's actually very simple, because now we can think about each one of these in turn. Let's start with the I hat dot I hat. What is I hat dot I hat? Well, we are dotting a vector with itself. And we remember that when we dot a vector with itself, we get the square of the length of that vector. Well, what's the length of I hat? Is 1, of course, and the square of 1 is 1. So that means that that turns into just v1, w1, and that one factor there just goes away since that's 1. Good. Let's move on to the next one. When we look at that one, we have something different, because here we have a j hat dot I hat. Well, what do we know about j hat and I hat? They're perpendicular, and we know that the dot product of two perpendicular vectors is always 0, which means that this term just disappears. Good. Let's move on to this one. Here we have again, same problem. I hat dot j hat is 0, so this term disappears. And now we're left with this one right here. J hat dot j hat, that's the length of j hat squared, which is 1 squared, which is 1. So this whole thing just collapses to v2 w2. And now we have a very simple formula, because we have that the dot product of v and w is just this thing right here. Let me rewrite it up here. So we have our second formula for the dot product. This one allows us to compute the dot product explicitly when we know the components of our two vectors. To find the vector's dot product, we just multiply the first components, multiply the second components, and add the two things together. It's as simple as that. So for example, if we had 1, 5 dotted with -2, 7, the dot product immediately we would find is 1 times -2, which is -2, plus 5 times 7, which is 35, which is 33. Easy as that. I should mention that the derivation that I gave a moment ago works no matter how many components we have. So for example, even if we were looking at vectors in three-dimensional space and we had something like 3, 5, 2 dotted with 0, 1, 5, we could still compute the dot product in the exact same way. 3 times 0 is 0, 5 times 1 is 5, 2 times 5 is 10, so the dot product of those two vectors is 15. Let's put these two formulas to use with a simple problem. Let's find the angle between these two given vectors in three-dimensional space, or in R3, as we sometimes call it. This isn't necessarily even a very easy problem to visualize, because if I have my coordinate axes here, 2, 3, -1, well that's, 2, 3, that's somewhere down here below the xy plane, and w is 1, 0, 4, that's somewhere up here. Very hard to visualize these things. And we're looking at the angle between those things, and the perspective is all skewed, so I don't know, I'm guessing it's probably a little greater than actually it must be a little bit greater than a right angle, but we'll find out. We'd like to be able to get it more exactly. Anyway, we can do this quite easily with our two formulas, because on the one hand, we know that v dot w is 2 times 1, which is 2, plus 3 times 0, which is 0, minus 1, or plus -1 times 4, which is -4, which when we put all that together, we get -2. Okay, actually the fact that the dot product is negative tells us this will indeed be an obtuse angle. So let's see, how obtuse will it be? On the one hand, we know this. On the other, we know now that -2, which is the dot product, is also, by our first formula, the length of v times the length of w times the cosine of the angle between those two vectors. Okay, let's see. What can we do here? Well, the length of v, we can get the length of v because we found a formula for it in the previous video. If this is v, we can compute very easily. The formula for that thing is going to be the square root of, let's see, the sum of the squares of the components. That's going to be 4 plus 9 plus 1, which is the square root of 14. And similarly, the length of vector w is going to be the square root of the sum of the squares of its components, which is going to be 1 plus 0 plus 16, which is 17. And then we still have this cosine theta hanging over, which is good because that's what we want to solve for. Well, now we have this equation. -2 is all this junk, and that's what you learn algebra for, because we can now solve for theta. Solving for theta, we get that theta is going to be, let's see, the inverse cosine of -2 over the square root of 14 times 17. And if you run that through a calculator, you will find that that is about 97.4 degrees. This is great. We can already see our hard work in developing properties of the dot product paying off. If I had asked you when you first met the idea of vectors to find the angle between these two vectors and you didn't know anything about the dot product, it would have been quite a pain. Not that much of a pain. You would have had to use some trigonometry, in particular the law of cosines. Speaking of the law of cosines, you might not remember how to derive it, how you derived it when you took trigonometry long ago. You might not even remember exactly what the statement of it is. Hopefully you at least remember what it does. Given any triangle whatsoever, it gives you a relationship that's kind of like the Pythagorean theorem, which relates any side of your choice to the other two sides and the angle opposite the side of your choice. Why do I bring that up here? Only because there is a nice way to derive the law of cosines using properties of vectors and the dot product in which you just follow your nose. There's really no cleverness involved whatsoever. So I'll show you how that works. The idea is, instead of thinking of a triangle, as we have here, we're going to reconstruct the triangle, but using vectors. It may not look exactly like the one I have there, but that's okay. So let's see, I have two vectors, and these will represent two sides of our triangle, and I'll call this one vector A and vector B. Now, if I do that, the remaining side, which maybe I'll draw right here as this vector, that is going to be A minus B. You can verify that very quickly because you can see that B plus A minus B, of course, should be A, and it is if you add those things tip to tail. Anyway, I know that in the law of cosines, I'm ultimately looking for something like c squared is a squared plus b squared, and then there's some weird thing involving this. Hopefully you know what it is. It should be minus 2ab cosine that, but even if you didn't remember that, you'd say, well, it's c squared is a squared plus b squared, like the Pythagorean theorem, and then there's that weird error term involving the angle. So let's see what we can do. Well, we're looking for something about the square of this side. So in other words, we're looking for something about the square of the length of a minus b. Okay. Oh, we know something about the square of the length of a vector. That's the same as the dot product of that vector with its self. And this looks familiar. This looks like something we did a moment ago. We know that we can simplify this expression by using the distributive property of the dot. We could think of this as one piece and distribute the dot like that. And then we would end up having to distribute the dot again. And I'm going to leave those details to you, but you should see that when it all works out, what we're going to end up with is we're going to have A dotted with A, which is going to be A dot A, but another way to describe A dot A is the square of the length of A. We're also going to end up with minus B dot minus B, but those minuses get pulled through the dot, become a plus, and we get B dot B, but B dot B, you dot something with itself, that's the same as squaring the length of that vector. We're also going to get an A dot minus B and another A dot minus B. So we're going to end up with two copies, we're subtracting two copies of A dot B, or we're adding two copies of A dot minus B, and I've pulled that minus through the dot product as we discovered that we could. Well, we're practically there. Because let's just look at that last term. What's A dot B? One thing we know about A dot B is that it can be represented as the length of A times the length of B times the cosine of the angle between A and B. And I called that gamma over here, so I better call it gamma over here. So that's going to be cosine gamma. And now, that is basically the law of cosines. If we were to translate this over and think of these not as vectors, but just think of this as side A, side B, and side C, that would be telling us that the square of C is the square of A plus the square of B minus 2AB cosine gamma. And that is your old friend, the law of cosines. Now very easy to derive thanks to these properties of vectors and the dot product in particular.